Hello, in this episode, we are going to talk about principal component analysis. So what are principal components? These are a sequence of linear projections of the data, mutually uncorrelated and ordered invariants. And then you might be wondering, what? And that doesn't sound like plain English, okay? So here in this episode, I'm gonna explain what does it mean, why do we need these principal components, and how do you actually compute the principal components? Okay, here's the motivation. So suppose we want to examine, let's say, three data set with three features, let's say age, gender, and IQ. And plotting like the two-dimensional scatter plots, how many do we need? Age, gender, IQ, gender, IQ. We need three scatter plots to see and examine the data. Fine, that's doable. What if we have 10 features, age, gender, IQ, income, education, blah, blah, blah. If you have like 10 of them, how many two-dimensional scatter plots do you need? 45. In general, if you have like P features, then you need P multiplied by P minus 1 divided by 2, like the combination. Okay, that's a lot, isn't it? What if you have 20? I mean, I don't want to even think about it. Okay, so when there are many features, like the P is very large, then it's impractical to look at all 2D plots. And usually we get a good sense of how the data looks like with 2D plots, for example, isn't it? Also, if you have this many features, then none of these two-dimensional scatter plots are likely to be useful. Why? Because each plot will just contain a small fraction of the total information. It doesn't really show the whole picture of the data. So what people think would be nice to have is that a low-dimensional expression that captures most of the information. Can we somehow shrink these like 10 variables into some representative, let's say 2 variables, yet contain most of the useful stuff in the data? And that's where the PCA comes in. It's like a tool to efficiently extract information using a small number of synthetic features. And synthetic means that we actually make a linear combination of these many other variables. So meaning 0.1 times age plus 0.2 times gender, 0.5 times IQ, blah, blah, blah. So we pick certain linear combination of these existing variables. Okay? But we happen to choose these weights in a way that it's best efficiently collecting the information that is actually in the data. So as if it's like almost as good as picking using all the 10 variables, we can just use, let's say, 2 variables of the synthetic variables. Okay, so as I said, it seeks a small number of synthetic, like a linear combination of features that capture most of the information. And most information in a sense that the data varies the most. So along that particular dimension, if you change the value of that particular synthetic variable, the outcome variable will change a lot. Okay, so for data set of P features, there are at most P principal components. So if you have 10 variables, then at most you can construct 10 distinct principal components. And the reason is because they have to be orthogonal to each other, which are ordered in decreasing variance, meaning the largest variance first. And the larger the variance, more information it contains. So we tend to like, if we construct, let's say from 10 variables, we construct 10 principal components, we tend to pick the larger 3 of the principal components with the largest variances. Okay? So for example, the first principal component of P features is the normalized linear combination. Normalized in the sense that we want the weight squared sum will be 1. And pick a linear combination, and that has the largest variance. In the second principal component, naturally we would then have the second largest correlation, but also it has to be uncorrelated with the first one. So it takes some math to do that. Okay? These weights happen to be called the loadings. Okay. And the principal component, so for example, if you observe one particular person's data, like age is 65, income is $50,000 and blah, 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 and you use those loadings, the weights, construct it, and then come up with this element of a principal component, it's called a score. So these are just notations. Okay? So pretty simple. The question is, how do we get those weights, isn't it? To maximize the variance and orthogonal. There seems to be a lot of strings attached. How do we get them, isn't it? It turns out very simple. The eigenvector comes into the game. It turns out that these loadings are eigenvectors of the correlation matrix. What's the correlation matrix? Well, it has to be first D mean. So if there's the average X variable or many variables, get the mean, subtract the mean from that variable. So it has a zero mean. And then have this multiply it. So you get the correlation matrix. So that will be a square matrix, isn't it? It's a P by P square matrix. If you have P elements, and get the eigenvalue and eigenvectors. The eigenvectors are the loadings, and the eigenvalues are the variance of it. Okay? So again, the process is mean the features, get the correlation matrix, get the eigenvectors, and the principal component is the linear combination of those. So there are at most P principal components, isn't it? Because of the linear combination, there are P eigenvectors at the most, and there are P principal components at the most. Okay. Here, let's look at our real data. So I happen to prepare one here. So we are going to use the medical insurance premium data, which is a big business in finance. Okay. Okay, so medical insurance premium data, and if you click download, it will get you the medical premium data, which looks like here, age, diabetes, blood pressure, and blah, blah, blah. And eventually there's the premium price. This we will not use. We're just gonna play with up to J column. Okay, premium price is eventually what we want to predict. So go ahead and download data, and then with the medical premium. I'm going to clean up the data. I'm going to make a lowercase. So there was some capitalized headings, so I'm going to make it lowercase. And drop the premium price. Again, that's not what we want to use it as an X variable. And convert to NumPy. Standardize the data, meaning at least you should d-mean it. So get the mean and standard deviation of each columns, and then subtract the mean and divide it by the standard deviation. So all the variables, if you want, you can take a look at. All the X variables will look like somewhere ranging between close to -1 to 1 most of the time, isn't it? Okay, so now I get the d-mean variable X. Let's get the correlation matrix, transpose of X multiplied by X. Okay, so that's a matrix. The eigenvalue will be the weights for the principal components. And there are, well, how many columns do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we have 10 columns. So there will be 10 eigenvectors and eigenvalues. Okay. How about we just pick the two largest one? Okay, so these are the two largest eigenvectors. Okay, so there are 8 more eigenvectors, but we happen to just pick the two largest eigenvectors. Okay. And then the principal component is multiplying that X with this eigenvector, and you will get, well, the original data was 986 columns, rows, and we just have only 2 columns, meaning the original data is a 10-column data. It's 10 variables to express the data, but now we're shrinking it down to 2 columns, 2 variables, the principal components, which are the linear combination of the original 10 variables. But we just happen to pick the linear combination smartly so that it will contain most of the information that's contained in the 10 variables. Pretty neat, isn't it? So this explains what our principal components are and why it's useful and how to get it running on Python. Thank you for watching the video.